Hi there. I'm going to now jump into slide 9, question 2, part A and B, and move on here. Just an FYI, I recorded all of this and it ended up being over an hour and a half long. So I'm re-recording it. Hopefully it's simpler. Hopefully I don't miss some of the golden nuggets of information that were in the last video, but you'll be awake. So that'll hopefully be better. So I'm going to try to keep this under a half hour. Let's go. All right. So first thing here is 10.33333. The way you say that is this 0.3 bar. And the way we make that symbol is by typing the 10 and then 0.3 equation editor. This symbol right here, bar accent over the 3. Okay. So it's 10.3 bar. That's how we get that. Okay. So in order to convert terminating decimal number into a fraction, try converting a repeating decimal number into a fraction. Repeating decimal numbers are more difficult to convert into fractions. First step is to assign the given decimal number to be equal to a variable x. So assign the given decimal number to be equal to the variable x. For example, decimal number of 0.3 bar, or repeating, is x equals 0.3 bar. If x equals 0.3 bar, or repeating, what does 10x equal? So 10 times 0.33333 equals 3.33, or 3.3 bar. So if x equals 0.3 bar and 10x equals 3.3 bar, I want to zoom in on this for a little bit here, and 10x, so then what they want us to do is subtract x from that equation. Essentially, we took x, multiplied it by 10, and got 3.3 bar. Now they want us to subtract 1x. So 10x minus x equals the same as 3.3 bar minus 0.3 bar equals 9x, because 10 minus 1 is 9, equals 3. So 9x equals 3. See? Now, if you solve for x, what is the result? So in order to solve for x on this, 9x divided by 9, 9x divided by 9, 9 would equal 1x. So 1x, because 9 divided by 9, it's actually easier if you see this as the big division, the fraction. Okay, so 9x divided by 9. Okay, so 9x divided by 9 equals 1x, which still equals 3. Equals 3. On paper, I would highly recommend you just keep this all nice and lined up on paper. On here, it's not so easy. So 9x equals 3. 9x divided by 9 equals 1x. equals 3. So x equals 3. See? So recall the value assigned to x using in part A. Using the solution for x that you found in part C, what is the fraction that equals the repeating decimal 0.3 bar? So right there, 1/3. See, 1/3. Evaluation. I had to figure out how to use this bar to be able to explain that, and I got confused. So now I understand what they were trying to do was show us that this as a fraction, when compared to 10 times the amount, was a little
We've
confusing.
converted decimal numbers with one repeating digit, such as 0.3 repeating, into fractions. But what if the repeating decimal number has a couple of digits that repeat? Let's convert the repeating decimal number 0.27 repeating to a fraction. Set x equal to 0.27 repeating. We'll call this equation 1. X equals 0.2727271. Find the power of 10 that you can multiply x by so that the first iteration of the repeating numbers, 2 and 7, is on the left side of the decimal point. Multiply the equation 1 by powers of 10. 10x equals 2.72727.
That wasn't enough.
100x equals 27.2727.
That worked.
Multiply 0.27 repeating by 100 to get the first 27 on the left side of the decimal point. We'll call this equation 2. 100x equals 27.27 repeating 2. Now, to get rid of the repeating 27, subtract equation 1 from equation 2. 100x minus x equals 27.27 repeating minus 0.27. Solve for x. 99x equals 27. X equals 27 divided by 99. X equals 3 divided by 11. The number in fraction form is 3 over 11. 0.27 repeating equals 3 over 11.
So they took the the decimal form of 27, 27, 27 repeating and made it into a fraction. Now, 27 over 99, so they remember they divided by 99 to get rid of the 99 times x. So they divided it over here. What you do to one side, you do to the other. Then they reduced it. 27 divided by 9, because there was 99 here. 27 divided by 9 is 3. 99 divided by 9 equals 11. That's how they got the 3/11ths. 3/11ths is the same as 27 repeating. It's close. Okay. So, type the correct answer in the box. Use numerals instead of words. If necessary, use a slash mark for a fraction bar. Which fraction is equal to 0.13 repeating? 13 divided by 99. Okay, so here's the explanation. X equals 0.13. We multiplied it by 100 because this is the 100th place, and we got 13.3 repeating minus the 0.13 repeating, the 0.13 repeating, to get 99x equals 13. X by itself is 13 divided by 99, or 13 over 99. Irrational square
roots. We can express rational numbers as either terminating or repeating decimals. However, there are some real numbers that we can't express as terminating or repeating decimals. We call such numbers irrational numbers. The most common irrational numbers are roots of non-perfect squares and cubes. Irrational numbers have decimal expansions, but the digits do not terminate or repeat. Take, for example, the square root of 2 equals 1.414213563099504. This decimal number continues forever and does not repeat itself. In such cases, we can write only the approximate value of the irrational number. So, we write the number in an approximate form. The square root of 2 approximately is equal to 1.414.
How does that look on a calculator? 2, the square root is 1.414, blah, 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 blah. So that means to say that if we wanted a 2-inch squared tile, the length of each side would be 1.414 about inches long. So 1.414 times 1.414 equals almost 2. Approximate.
We can see that both 3 is greater than 2 and 3 squared is greater than 2 squared are true. This confirms the two statements. Watch the video on the next screen to see how to apply these principles to irrational numbers.
This is a way of saying that if 9 is greater than 4, then the square root of 9, which is 3, and the square root of 4, which is 2, that means 3 is greater than 2, and so on.
Hey, buddy.
Hey, bro.
What are you up to?
I'm looking at a number line for class.
Oh, hey. Number lines are way cool. They let you visualize the relationships between numbers, and they're infinitely small.
Infinitely small? That's trippy.
What I mean is, when you look at a number line like this one, it's pretty simple. It goes from 0 to 10.
Bro, I can count.
No doubt. But let's zoom in on this section between 0 and 1. Now we can see all of the tenths illustrated along the way. So we've got 0, 0.1, 0.2, 0.3, and so on.
Whoa!
Now, let's zoom in on the section between 0.6 and 0.7. On this number line, we can see all the hundredths between 0.6 and 0.7, like 0.65, 0.66.
Bro, it just keeps getting smaller and smaller. It's like we're zooming in on atoms and stuff.
We can zoom in even further. This number I've got highlighted is 0.683.
So, this is cool and all, but what can I use these number lines for?
Well, what about the square root of 3? Let's say you want to estimate it.
Why would I need to estimate it?
Buddy, the square root of 3 is an irrational number. It's easier just to estimate it.
Groovy. Can you show me how?
I sure can, buddy. Let's take another look at the number line. So the square root of 3, we know it falls between the square root of the perfect square 1 and the square root of the perfect square 4.
Oh. And how do we know that, bro?
Buddy, because 3 falls between 1 and 4.
Oh, right.
We know that the square root of 1 is 1, and the square root of 4 is 2. So the square root of 3 must fall between 1 and 2 on a number line. But where between 1 and 2 does it fall?
Oh, I don't know, bro. You tell me.
Don't worry, buddy. I will. Let's pick a decimal number between 1 and 2, like 1.7. What's 1.7 squared?
1.7 times 1.7 carry the 4. Looks like 2.89.
Good job. Since 2.89 is less than 3, we know the square root of 3 must be greater than the square root of 2.89, which is 1.7. What about 1.8? What's the square of 1.8?
You're killing me, bro. Hold on. Carry the 6. It looks like 3.24.
Good going, buddy. Since 3.24 is greater than 3, we know the square root of 3 is less than the square root of 3.24, which is 1.8.
So, using this number line, we can estimate that the square root of 3 is between 1.7 and 1.8, right?
You got it, buddy. Want to keep going?
We can?
Sure. Since the square root of 3 is an irrational number, we can keep going for a long time.
But we're just estimating, right? I thought we were just estimating with the number line.
We are, buddy. We are.
Well, between 1.7 and 1.8 is close enough for me. I've never been more precise in my life.
Somehow, I believe you. And it's all thanks to number lines and the square root of 3. Since 2.45 was only slightly too high, our next guess is 2.44. The square of 2.44 is 5.9536. This is farther from 6 than our last guess. Therefore, the square root of 6 is approximately equal to 2.45. Guess 2.44. Check. 2.44 squared equals 5.9536.
This is farther away from 6 than our last guess. Therefore, the square root of 6 is approximately equal to 2.45.
Decimal expansions of irrational numbers help us make correct estimates in real-life situations too. Let's look at an example. Warren is tiling his bathroom. He wants to cut 3 different sizes of square tiles. Tile A must be 5 square inches, tile B must be 10 square inches, and tile C must be 15 square inches. Warren needs to know the side length of each of the 3 tiles. His tape measure shows 1/16 inch increments. Next, you'll help Warren find the length of each tile using his tape measure.
So in the first part of the activity, we're going to guess and check. I can guess that 2 squared is 4, right? Because 2 times 2 is 4. But I need 5 square inches. If I put 3 in the guess, then 9 comes out because 3 times 3 is 9. And so the first one needs to be 5 square inches. So I can't go, I got to do more than 2 but less than 3. So then I put in all these guesses, and all I do is do like 2.3 times 2.3 equals 5.29. So I'm still too high. So if I look at the sample answer, I get all these guesses that just get closer and closer and closer and closer and more zoomed in until we get really stinking close. Square root of 5 is approximately 2.23607 inches. We do that for 10 square inches as well. I guessed, since I know that 3 times 3 is 9, which is too low, maybe 3.5 times 3.5 would be close to 10, but it turned out it was too high. So I brought it down. I half-stepped it. Half of 5 is actually 2.5. So, because it's 3.50, so half of that would be 3.25. Hope that makes sense. So we're trying to get closest to 10 as possible. We noticed that this went a little too low, below 10. So then we bring it back up. Now 3.16228 S times 3.16228 gets us 10.00000. That's about as close as we can possibly get. See the sample answer. They go through the guesses and the checks to get that answer. This is boring. This is dull. This is not something you would probably do in the real world, but it's what is necessary for this question. And the real world component comes in. So you'll want to tile your living room or
Decimal expansions of irrational.
you want to tile your bathroom, or you want to work as a labor tiling your bathroom, and you have to cut these tiles with a tile saw or a tile cutter, and the boss, because they're the boss, or the homeowner, because they pay the boss, says, I want all my tiles to be 5 square inches, 10 square inches, and 15 square inches. Why? I don't know. Why do people do what they do? It doesn't matter. That's what the customer wants. So what is the length of this side and this side? What is the length of this side and this side? What is the length of this side and this side? And we can guess. We can do this guess and check with our calculator and figure that out. Now, there are other math ways of figuring it out too. By the way, in order to get that, what was I thinking? What symbol? Okay, well, I can't remember what symbol I was looking for.
In the lesson activity, you found the approximate lengths of 3 sides of square tiles. You rounded these lengths to 5 decimal places. However, Warren's tape measure is marked in increments of 1/16 inch. So, he needs to find the measurement to the nearest 1/16 inch that is closest to the decimal approximations you found. In the next lesson activity, you'll estimate the length measures to the nearest 1/16 inch. Then you will use your estimates to find the actual area of each tile.
This tells you what we're doing for the next activities. The next activity is essentially saying if it's 1.375 in decimal, 1.375 is how many sixteenths? Because this is the closest we can get right here. I can't really get closer and be accurate. My precision, as it will mention later, is this is as small as I can get. One little measure right here. So is it closer to here or closer to here? That's what we're going to figure out next. So we do that by taking the decimal part. We already know that if it's 2 inches, it's going to be closest to the 2 point what? So we don't need to figure out how many sixteenths are in the 2. We just need the part after the decimal. Now, the problem, in order to do that, is to divide this amount by 16, or 1/16 rather. In order to get rid of this 1/16, we have to multiply it. I'm not really sure exactly how that mumbo jumbo works, but when you multiply 0.23607 by 16, you're undoing this right here, this whole thing, and getting it where we know how many sixteenths there are in this. In this case, there are 3.77712 sixteenths. Well,
in the lesson activity, you found the
I can't measure 1, 2, 3.77 sixteenths, not quite 4 sixteenths. I can do 1, 2, 3, but I can't measure 0.77 right here. That's 77. So I just round up to 4. So 1, 2, 3, 4 sixteenths is the same as 1/4, just so you know, because this is a half, this is a quarter, this is an eighth, this is a 16th. So we now have 3.77. We round up to 4, so 4/16. So the actual measurement on the measuring tape would be 2.23607 is approximate. It's close to 2¼ inches. So then they want us to do the same thing with tile B. So 3.16228 divided by 1/16 magically somehow is multiplied by 1/16. So 0.16228 multiplied by 16 equals 2.59. We would round that up to 3. So it would be 3 3/16. 3 3/16. Check our sample answer. 3 3/16 is correct. 3 divisions. We round that up because we can't measure to the 5/9 or 0.59 of a 16th. Our tape measure doesn't work that way. Same process for tile C, which is the 15 square inches. Each length of a side would be 3.87298 if we could be super precise and super accurate, but we can't. We can only measure to the 16th on the tape measure. So, same thing, multiply by 16, we get 14/16. I think that divides or breaks down into 7/8, but they keep it as 14/16, 3 14/16. So on the tape measure, you would be almost all the way to 4 inches, but it's 2/16 less, just so you know. Okay. So question 2 says, using the estimates you found in question number 1, convert the lengths into decimal numbers. So we're going to take the approximates, 2¼ and convert it into a decimal. So what is 2¼ converted to a decimal? If you remember from before, we converted decimals by doing 1 divided by 4 equals 0.25. So 1/4, 1 divided by 4 equals 0.25, and then the 2 stays. So then what is that squared? It's actually 2.25 times 2.25 gets us the square inches of 5.0625. So the customer asked for a 5 square inch tile. This is as close as we can get with our measurements. The next one is 3 3/16. So that would be 3/16, 3 divided by 16 equals 0.1875. So 3.1875 times 3.1875 equals 10.160. So basically 10.160 square inches. And this shows the math for each of those. Feel free to pause it so you can double check. Estimated length is 5 4/5, which is 2.25 inches, which is 2.25 inches times 2.25 inches is a total of 5.0625 square inches, etc. for tile B, etc. for tile C, and you continue on. Evaluation. This is real easy to get lost. it's real easy to forget what we're doing and what the numbers mean. So I highly recommend you using a pencil and paper and keep those equal signs straight up and down and label what it is you're talking about.
Because irrational numbers don't terminate or repeat, we cannot find exact decimal expansions for them, so we have to estimate their decimal values. Sometimes there is a set amount of accuracy, such as when the lesson activity required estimating the length of the tiles up to a precision of 1/16 inch. Set the precision needed based on the situation. For example, estimating to the nearest tenth of a mile is fine when estimating the speed of an ant, but we wouldn't want to estimate the speed of an airplane to the same level of precision. Some commonly used irrational numbers that we round off to various levels of precision are pi, the golden ratio, and Euler's number.
So in mechanics, when you are measuring for machining parts, it might be within the millimeter or something even finer of precision. Okay, so this says, what is the value of the square root of 7 inches to the nearest hundredth? So 7, the square root of, and the nearest hundredth. It's 2.64, that's the hundredth place, but that 5 we round up, so it's 2.65. Check. That explains it. It's approximate. How do we show the approximate symbol? I'll show you on the next example. Oh, I won't show you on the next example. Let me go back.
Because irrational
I'm only going back to show you how to make this symbol, in case I forgot to show you. This symbol is right here. What? No, not a picture. It's in the editor, and it is right here. This is the approximate. All right, so it's almost equal to. Not equal to, but almost equal to.
because
We can classify real numbers as rational numbers or irrational numbers. Rational numbers are numbers in the form a over b, where a and b are integers and b does not equal 0. We can express all rational numbers as terminating or repeating decimal numbers. Roots of non-perfect squares and cubes are examples of irrational numbers. We can also express irrational numbers as decimal numbers, but they neither terminate nor repeat. We cannot get the exact decimal expansion for irrational numbers. So, we round them depending on the precision that's needed for the situation.
Congratulations, you completed the tutorial for real numbers. I highly recommend you go back and watch both videos when completing the guided notes. This is difficult content in that there are lots of steps. Please don't hesitate to ask for help. I am sure I can confuse you further. Here's to your greatness of perseverance through this lesson. Thank you.